talk about 2.2 characteristics of quadratic functions, and a bunch of vocab and different review information reviewed from Algebra 1 here. So first, axis of symmetry. Our axis of symmetry can be found by doing, well, let's do it pictorially first. Axis of symmetry is the line that splits your parabola in half. Okay, it's your line of reflection. So for instance, your vertex lies on it, and a point to the right, say the ordered pair 2, 3, can be reflected over that, and that would give you the ordered pair 0, 3. Okay, so the axis of symmetry allows you to just really graph one side of your parabola and then reflect it over. It also helps you to find the x value of your vertex, which in this case your vertex being 1, 2. Okay, the axis of symmetry, depending upon what form you're in, we find in different ways. If we're in standard form, there's a formula for it. If you're in vertex form, it's easy to find based on finding the vertex. And if you're in intercept form, we have another format for it. But at least pictorially, here's our axis of symmetry. It has an equation of x equals 1. So make sure you always label your vertex, or excuse me, your axis of symmetry in the form of x equals. So in this case, x equals 1 is the equation. You can't just say 1. If you say 1, you could be referring to y equals 1 also, which would definitely be incorrect. So you for sure want to call it x equals 1 there. All right. Next thing is your vertex, which we talked about already a bit, but your vertex is the lowest point, or the minimum value, or it could also be the maximum value of your parabola. So in this case, this parabola opens upward, so our vertex is called a minimum point. It's the lowest point on the parabola. It's also the point that lies on the axis of symmetry. Okay, it's in this case also known as a minimum, since it's the lowest point of the graph, which kind of covers our next term here as well. Now I'm going to draw another real quick parabola here. Let's say my vertex is here. All right, and I kind of do something like this. Well, this parabola right there, quick sketch, and this has a vertex up here at -3, 1. My throat there. Vertex at -3, 1, and it's a maximum value because it's the highest point of our graph. Okay, so it's called a maximum. All right, so a little information about increasing and decreasing. We will talk about when our graph increases and decreases, and use this in calculus a lot more. But if you think of a graph, reading it from left to right. So always read your graph from left to right. So I'm starting at the far left point on this original graph and moving to the right, just kind of like reading a book. Okay, if I pick my graph from the left and start reading it to the right, you'll notice I am sliding downward, or I am decreasing. Okay, so my graph is decreasing on this side of the axis of symmetry. All right, so in my original graph, it is decreasing on this side of the axis of symmetry. Okay, and then if I look at the other side over here, I'm reading my graph, I am now going upward. So if I'm reading that graph, it is increasing on this side of your axis of symmetry. Okay, and so kind of like the coloring here. Yeah, right? It's increasing over here. All right, and so the way we label that in this case for the original graph I had there, not the one that I drew, we would say my graph is decreasing. Oops, excuse me. We say that my graph is decreasing when x is, so if I look at my x value, we judge it based on the x-axis here. Okay, and so based on the x-axis, we're decreasing over here, okay, on this side, the yellow portion here. So we're decreasing when x is smaller than 1. So notice the axis of symmetry is at x equals 1. So we're decreasing to the left of that, on the left-hand side of that, so when x is less than 1. So think of it this way. Over here, from the vertex, think of it this way. From this side, we're decreasing on the left of that. X is less than 1. We're increasing over on the right-hand side. So that means we're increasing to the right. Notice my arrow points to the right when x is greater than 1. Okay? That is increasing and decreasing. And we, like I said, you use that a little in calculus when you talk of points of inflection and stuff like that. For now, we're just identifying that to kind of get you prepared there. All right. One other piece of information, domain and range. Those terms hopefully sound familiar, but really you could figure out your domain and range by looking at your graph and thinking to yourself, okay, first of all, domain stands for x, range stands for y. Okay, and you're talking about your x-axis, using your x-axis to judge that, or your y-axis to judge range. All right, and so upon the x-axis, you've got to ask yourself, is there a value on the x-axis that my graph will not exist for? Or another way to think about it, if I keep going with my graph to the left, notice I have arrows here, I keep going to the left forever and to the right forever, will my graph ever have a place on x where it will not exist? And in this case, it won't. It keeps extending to the left and to the right. In fact, it'll do that for all parabolas. And so when it extends to the left and the right forever, my graph is extending leftward forever and leftward forever and rightward forever. That means my domain is all real numbers. And I like to use that little abbreviation there. You could also write out all real numbers. All real hashtags there. You could probably spell out the word numbers, but all real numbers. Now, in terms of the y-axis, you gotta think. I like to read my arrows. So, for instance, this arrow is going out to the right and upwards. This arrow is going out to the left and upwards. So my graph extends to the left forever, and my graph extends to the right forever based on that arrow. It also is extending upward forever at both of those arrows, meaning my graph is going upward forever. It is not going downward. Okay, so you'll notice in terms of directions, left, right, up, down, we've talked about it going to the right forever and to the left forever. That was the all real numbers, moving left and right. Okay, and we've now talked about it going up forever. We haven't talked about it going down at all. So that means my graph extends from the lowest point, its minimum, on the y-axis, upward forever. Okay, and that would imply that my graph, or my range is y is greater than or equal to, greater than or equal to 1. So my graph could, not 1, excuse me, greater than or equal to 2. Okay, so my graph starts here on the y-axis at 2, and it extends upward forever. Okay, that means I could plug any value in for y, or excuse me, I could get an output value for any value that's 2 or bigger here. And my graph would exist for any value for y greater than or equal to 2. Notice the graph doesn't exist anywhere below 2. That is range. Now, I've spent a lot of time talking about these vocab terms because what happens here is when we're going through and graphing these different forms, standard form, vertex form, and intercept form, those are forms you should copy down and memorize. Those are the 3 forms of quadratics we're going to talk about. When we talk about each of those, we're going to reference each one of these terms. Okay? So I'm just going to go with the assumption that we kind of understand these terms now. We have these forms. Y equals ax squared plus bx plus c for standard form. Y equals a times x minus h quantity squared plus k for vertex, and y equals a times x minus p quantity times the quantity x minus q whoa, there should not be a quantity squared there. Why don't you just kind of get rid of that squared? Good thing we talked about it. No squared on that one. Okay, just a typo. All right, so we have these different forms that we're going to go through, and I'll describe them as we graph them. So let's start with standard form. So we're going to graph the form, or graph the equation y equals 3x squared plus 6x plus 1. And the first thing I like to do is identify my a term, b term, and c term when I'm in standard form. Please note that when I have identify a, we're identifying the coefficient or the number in front of x squared, not the x squared itself. And when we identify b, we're talking about the coefficient or the number in front of the x. Once again, not x itself. So we don't include the x when we say b is 6 and c is 1. So that should be an A. There we go. All right. And so since we're dealing with standard form, we actually have an equation that we use for axis of symmetry. It's x equals the opposite of b over 2a. The opposite of b over 2a. So that means if I were to plug in or substitute in the value for b and the value for a into this equation here, we would be able to figure out the axis of symmetry, which helps us out because it kind of gives us a starting point when graphing. So negative b, so negative b over 2 times a. And that's why I identify a, b, and c really quick here. That gives me negative 6 over 6, which is 1. So my axis of symmetry is x equals 1, and that's what we should have identified there. X equals 1. All right. Now let's make sure I didn't make any mistake. Oh, I did. See? Always double check. Negative 6 divided by 6 is actually negative 1, so x equals negative 1. So got everything plugged in correctly. You definitely want to make sure you don't make a mistake at the very beginning. Otherwise, you finish graphing and you're like, you may try to substitute something in and find out it doesn't end up on your graph, and then you find out, man, you made a mistake at the very beginning. So we got x equals negative 1 there. That's our axis of symmetry. All right, the vertex lies on the axis of symmetry all the time. Okay, and that's one of the benefits of finding that, because the vertex, the actual formula is saying, well, if I know the axis of symmetry, negative b over 2a, that's my x value. So note my x value of my vertex has to be on negative 1. So I know in this case the vertex is negative 1 for x. These are always the same. And then to find the y value, you just do f of negative b over 2a. Now that looks way confusing, and I only show it because that's what most textbooks will do. And if you've done function notation, you know really all that means is I am taking whatever I got for opposite of b over 2a, in this case negative 1, and I am saying I am going to find f of negative 1 now. In other words, I am taking and substituting this into my original equation, except for x isn't going to be x, it's going to be negative 1. So I'll do that right over here, okay? I'll say, well, f of negative 1 is equal to 3 times negative 1 squared plus 6 times negative 1 plus 1. Okay? And then I do the math, I get 3 times 1. Note you actually square and then multiply by 3, plus negative 6 plus 1, which really this just means minus 6, right? So we have 3 minus 6 plus 1, also known as negative 3 plus 1, or we have negative 2. Okay? And so f of negative 1 is negative 2. So my vertex is negative 1, negative 2. And so I can go ahead now and go to negative 1 and negative 2 on y and plot a point. All right. Now you could create a table of values here and just start doing some substitution. And the tables that I like are my x, my y, and I like to have this h kind of picture here, and I like to put my rule in here. My rule is just the expression 3x squared plus 6x plus 1. Now, I'm not going to do this for all of them because I'm going to show you a shortcut, but this is your quick substitution, right? You know your vertex. That's right in the middle, so I'm going to put -1. And I know if my input's -1, my output's -2, and I could actually show the math here. I could say, well, that's 3 times -1 squared plus 6 times -1 plus 1, and do, I've actually done that right here, okay? And I know I'm going to get an output of -2, so it's going to give me the order pair -1, -2. All right? Now, but having this vertex, I know I want to find values to the left and to the right. So in this case, I'm just going to go ahead, well, that's -1, here's -2, and I'm going to go with -3. I'm just going to find two values to the left-hand side of it. So I go 3 times -2 squared plus 6 times -2 plus 1. Okay, well, and -2 squared is 4 times 3 is 12. 12 plus -12 in this case is 0, and 0 plus 1. Excuse me, let me make sure I did that right. I got 4 times 3, which is 12, plus -12, which is 0, plus 1 is 1. Okay, so I got an input of -2, an output of 1. Okay, I go over to -2, and I go up to 1, and there is a point. And no, I really, I could put in 0 up here, but I really don't have to show a bunch of work because my output is a reflection over the axis of symmetry. So I should be the exact same value in terms of y, right? This and this should be the same because they're reflections over this axis of symmetry. Okay, and -3, 3 times -3 squared plus 6 times -3 plus 1. Okay, so that's 9 times 3, 27, plus -18, which is -9, plus 1 is -8, I believe. You could just double check that. Make sure I did that right. So 9, 27, 27, and 18 is -9. And oh, that's +9 plus 1. Oh, that should be 10. Oh, my bad. See, you're always double checking your work, and see, that's something that's going to happen when you're doing the math in your head as well. So looks like we get 10 there. All right, and so I now have the order pair -3, 10, and I can reflect that over. So I'm 2 away from the axis of symmetry, so go 2 away, and that gives us at 1 also 10. So you have 2 more points, -3, 10, and 1, 10. Now, I realize that this is taking a while, and you're like, man, this is a lot of work, but I'm going to show you a quick shortcut in terms of graphing. But for now, we'll hit these points, okay, and didn't really hit that one all that well, but we'll call it good for what we've got on this one. All right, so we have our graph. All right, I've created its table of values. The other way to graph, just really quick, let me show you a quick shortcut. When you're graphing quadratics, really, if you think of it this way, if you start at the vertex, I'm just going to write it up here real quick. Start at the vertex. If you go over a certain amount and then up or down a certain amount, you can graph a quadratic really fast. So if I start at my vertex, in this case, I start right here, and I go over 1, okay? So I think of it this way. I go over 1. I move over 1. Then I'm going to go up or down. Oops. I'm going to go up or down whatever A is. Or excuse me, I'm going to go up or down whatever the square of 1 is. Okay? And so in this case, I'm going to go up 1. So if I go over 1, let me switch colors here. If I go over 1, I'm going to go up 1. Well, notice that didn't actually bring me to where I want to go. I've got to take that, and I've got to multiply it by A. And so in this case, A is 3. So I go over 1 and up 3. And that brings me to this point. And then if I go over 2, I'm going to go up the square of that, which in this case is 4. and then I'm going to multiply it by a. And 4 times a is, or 4 times 3 in this case, is 12. So if I go over 2, I can go up 12. Which brings me up to 10. And really, if I was going to go over another one, I'd go over 3, and I'd go up 3 squared, or 3 squared times a. Well, in this case, 3 squared is 9. 9 times 3 is 27. Well, that doesn't fit on my graph, right? I'd have to go over 3 and then way up 27, which would be like way, way up here. Okay, it doesn't fit. But that's just a quick way of graphing. If you know this pattern, you're going over 1 and you're going up the square of that value. So this would be 1 squared, and then multiplying it by a, this would be 2 squared, and multiplying it by a. Okay, and so that will be really helpful when you're graphing. Just as a quick shortcut. Now, I truly think students still need to know how to do a table of values, but boy, this is really saves you a lot of time. Okay, just kind of quick shortcut. All right, we're going to move on and quickly talk about maximum minimum. So in this case, this graph has a minimum. Minimum is at y equals -2. You could also put the ordered pair -1, -2. Okay, so it's a minimum. All right, it's increasing. Well, this graph, if we kind of go through this graph is actually increasing over, like if we're following our graph is decreasing here, and then on the other side, we're increasing. Okay, and so remember, we're going from left to right, reading that graph. So my graph is increasing to the right of -1. So it's increasing when x is to the right of -1 or greater than -1, and it's decreasing, it's going downhill, if you think of it that way, when x is smaller than -1. So you use the x value of your vertex, okay, to help you figure that out. All right. Your domain, well, your domain in this case, x is expanding forever. It's all real numbers. Your range is y is greater than or equal to the y value of your vertex. -2. That should be greater than or equal to -2. Okay, it's going upward from there. Okay, it's going up and to the right and left. It's not going down. So going up on y, going left and right on x, we're good. All right, let's try another one. We're in vertex form. Vertex form is really nice because it actually tells you the vertex. The vertex, another name for vertex, is HK. And when you're in vertex form, they identify H and K. Now don't get confused with the negative out there. Okay, when I look at this and I look at the vertex, my vertex is 1, 3. Okay, it's not -1, 3. The other way to talk about it, I mentioned in class, is whatever will make this quantity equal 0. Okay, so if I say, well, what will make that equal 0? Well, x minus 1 equals 0 when x equals 1. Well, that's actually the h value of your vertex. Okay, so 1, 3. So if this said plus right here, it would be -1 then. Okay, so just a quick just a quick side note, if this said y equals -3 times x plus 1 squared plus 3, okay, that would be a vertex, and h value would be -1, because -1 makes it 0. K doesn't change, it's still 3. Okay, so this is kind of, I mean, this is kind of like our dream, you know, like if we're kind of dreaming of math later and we want to kind of a what if. Okay, I don't want you to be confused and think that that's part of this problem. That's kind of a what if scenario. All right, it would give us a vertex of -1, 3. All right, So let's go back to actually real life here in terms of this math problem. Okay, so we have a vertex of 1, 3. And now remember, our axis of symmetry, x equals, we're not going to use opposite of b over 2a because we know that these two values are always the same. Okay, remember in our previous problem, these two were the same. We had -1 and -1. They were the same for axis symmetry and vertex. That holds true all the time. Okay, so if I were to go ahead and plot this, I can look at, well, I'm like at 1 and 3. There we got it. Having some major problems trying to graph today. There we go, 1 and 3. Okay, and in this case, notice my a term is negative. If a is negative, when a equals negative, the graph opens down. When a is positive, just like in our previous problem, the graph opens up. Now hopefully you remember that from when we did transformations of functions. This is just a reflection over the x-axis. Okay, so that's what the negative is. So it means I am actually opening downward with this graph. But I'm going to use my patterns. A is still the same, so if you recall what we just talked about, going over and then up or down, in this case down, right, because a is -3, I'm going to go over 1 and I am going to go down 1 squared times a, or times -3, which is -3. So go over 1 and down 3. That's my next point. Now I'm going to go over 2 and down 2 squared times a. Okay, remember this is our a term. So our a this time is still -3. So that's 4 times -3, which is -12. I really think that's all that's going to fit on my graph. Okay, so I go over 2 from the vertex. I start at the vertex each time and go down 12. Okay, and that's going to bring me to -9. Okay, double check and make sure 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Whoop, see, made a mistake again. Man, it's a good thing I'm always double checking here. Always good to double check, especially when I'm staring at a grid here for long. So 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I was off by 1 there. Okay, and so I have my axis of symmetry. At x equals 1, I have a graph that goes downward like so. Okay, and then I can reflect my points. And boy, messed it up again. Shemini. Well, at least I'm giving us a lot of different reasons to double check our work there. Good golly. That should be our point there. And it's a reflection, so all right. Hey, real time here, man. I'm not changing anything up. So there we've got it. Okay? And we have our quick graph. Now you could create a table of values. I'm fine with that, but in this case, do we have a maximum or minimum? Well, we have a maximum. It's the top of our graph. Okay? So maximum, our maximum is at y equals 3. Okay? If you think of our vertex, it's always that value. It's either going to be a max or min. Okay? And you could list the coordinates there. That is at 1, 3. But we're really focusing on that 3 there. It's increasing or decreasing. Well, looking at our graph, if we think of it in terms of our being on a graph, we're going upward to begin with, up until we get to the vertex. So on this side, we are increasing. Okay? And then if we go to the other side, so from there we start falling downward. So on this side, we are decreasing. Okay? And so if you start once again at that same point, x, So we're increasing when x is to the right, or excuse me, to the left of 1. Okay, x is to the left of 1. And we're decreasing in this case when x is to the right of 1. X is to the right of 1. Notice the arrow, right? Okay, so x is to the right of 1, or x is greater than 1, and x is less than 1 is the mathematical way to say it. Okay, our domain, which again is all real numbers. It's always all real numbers on a parabola. It'll always exist on the x-axis. The range, well, the range is starting at y, and it's going from 3, and our graph is extending left forever, right forever, and down forever. So that means it's going downward. So it's got to be smaller than or equal to 3. It's going down from 3, less than or equal. All right, one last piece here is called intercept form. And intercept form works like this. P and Q are our x-intercepts. So if you think back to factoring in algebra, if I said, well, I want to find out what makes this 0. So in this case, P is 3. And what makes this 0? Q is 7. So when P equals 0, okay, or not when P equals 0, when that quantity equals 0, okay? And so what I'm going to do is I'm going to take x minus 3, set it equal to 0. In this case, that would be when x is 3. So notice, that's our P value, okay? And x minus 7 equals 0. That's when x equals 7. Notice that's our Q value. What does that tell us? That tells you your y-intercept, okay? Or excuse me, your x-intercept. It means it crosses the x-axis at these points. Remember, factored form there. So we're going to cross at 3, and we're going to cross at 7. Well, how is that helpful? Well, these are reflections of each other, and they're reflections over the axis of symmetry. Think back to a parabola. Points have to be, if they're on the same y value, they have to be reflections of each other, okay? And so they're both 2 away from the axis of symmetry. That means our axis of symmetry is x equals 5, okay? And so another way to find that would actually be to use the formula P plus Q divided by 2. That's our axis of symmetry. So in this case, 3 plus 7 divided by 2, which is 10 over 2, or 5. Make sure you have that equals x. X equals 5. That is our axis of symmetry. And remember, vertex-wise, these are the same. That's 5. Okay? And to find my y value, well, to find y, it's a little tougher. You're going to actually have to plug it in. So you're going to substitute it in, do f of 5. So if I just take my equation, y equals negative x minus 3 quantity times x minus 7 quantity. Hey, remember, sorry, I made that mistake earlier as well. No squared on that. Remember, we fixed that on the other slide there. Okay, I'm going to go ahead and substitute in 5 for x and find my output of y. So when I put 5 in for x and 5 in for x here, really what I end up with is negative 2 and negative 2. Negative times negative is positive. We end up with 4. So now I have an input of 5. I have an output of 4. That means my function is right there. Or excuse me, my vertex is right there, 5, 4. Now, please note, hopefully you would be checking yourself and going, whoa, my A term's negative, right? You know, maybe rather than writing it even like that, maybe drawing an arrow like this. My A term is negative, meaning this graph has to open downward, which means my vertex better be above my intercepts. If my vertex was down here, the graph would have to open up. Okay, so but the vertex is up here, it's opening down. And it also holds true, A is negative 1. That means if I'm graphing it, I would go, if I'm using my patterns again, over and up or down, in this case down. Okay, you could make a table of values like we did the first time, but if I'm going over 1, I'm going down 1 squared times negative 1 times A, which is negative 1. So I go over 1 and down 1. And then I go over 2 and down 2 squared times -1, or 4 times -1, which is -4. Go down over 2 and down 4, which is that. Reflect them, okay? By the way, if I go over 3, I'm going to go down 9. Okay, it's going to put me down here at -5. And I'm going to reflect it. Okay, and then from there it'd be go down 16, which wouldn't fit on the graph. But if I'm graphing this, hit my points there the best I can. Okay, and done. Got our arrows. All right, this is obviously a maximum. It's a maximum at, let's go ahead and switch up colors here. Maximum at y equals 4, the ordered pair 5, 4. It is increasing. Okay, so if we look at our highlighter here, reading our graph, let's use a different color. Reading our graph, we are going upward up to x, so we're increasing on this side. Okay, oops. And then we are decreasing over here. Okay, so continue our graph, we're decreasing on this side. All right, and so looking at that, we are increasing when x is smaller than, notice there, 5 or less than 5, and we are decreasing when x is greater than 5. Okay, it all starts with that axis of symmetry. Domain, once again, all real numbers. Every x value would have a value for this function here. And our range starts at the vertex, the y value of the vertex. So y starts at 4, and notice our graph is moving downward to the left and downward to the right forever. So we've got the right and the left taken care of. The downward is the less than piece for 4. So when x is less than 4, but it could be equal to as well, right? Could equal 4, less than or equal to. And make sure we put that on it. Yeah, we did on our last one. Okay, so that is characteristics of quadratic functions. The only other thing I could point out is anytime you're doing story problems with these and you see the term find the maximum this, or find maybe the maximum profit or the minimum cost, when they talk about maximum or minimum, remember they are talking about vertex. Maximum and minimum, when you're dealing with story problems especially, refers to the vertex. Okay, that's just kind of a side note in terms of like dealing with story problems. Okay, so just add it to your notes somewhere. That's kind of a big deal. Whenever you're dealing with quadratics, you see a lot of times they bring up, hey, find the maximum. Maximum profit seems to be a big one you see a lot. Or minimum expenses. Okay, trying to maximize profit, minimize expenses. They're really referring to the vertex. Okay, that's it. Well, good lucky.